next goal is to take our description of factor groups in terms of fibers as elements and change it to a description of the same factor group, but now using cosets as elements. So let's start by just reviewing what is a coset of a group. This is something that we defined in the first video, but now it's going to become much more important. So let's take a subgroup n of G and an element little g. G times n is just the set of everything that is G times some element of the set n. This is the left coset of n containing G. We say containing G, I mean, since n is a subgroup, it definitely contains the identity. So this coset contains G times the identity, so it contains G. You can define right cosets completely analogously. Take NG is the set of everything that's something in n times G. That's the right coset of n containing G. An element inside of a coset is called a representative of the coset. So any x in Gn is a representative of the coset, or more precisely, a representative of the left coset of n containing G. So we saw in the previous video that if n is the kernel of a homomorphism, then we can see that G times n, this coset, is the same as x times n when you take any representative in the coset. We saw this first by saying we take any element in our fiber above A, and we can write the whole fiber as U times K, where K was the kernel of the homomorphism. So we saw that in the special case where our subgroup is given by the kernel of something, we can write the coset in terms of any representative of the coset. This is going to be true not just for subgroups that are the kernel of a homomorphism, but any subgroup. So we'll see that soon. But first, what I want to do is explain another description of the factor group. So let's say G is a group and K is the kernel of a homomorphism, phi from G to H. The set whose elements now are left cosets of K in G, where the operation is U times K, that's one element, times V times K, that's another element, is the coset UVK. So the product of the left coset of K containing U and the left coset of K containing V is the left coset of K containing U times V. That's going to be the definition of our multiplication operation. This forms a group. We're also going to call this the factor group. Use the same notation because we'll see that these groups are the same. The big thing going on in this proof is it better be the case that this operation makes sense, that it's well defined. So we took one coset multiplied by another coset, and that told us what coset we should get on the right. UK times VK is UV times K. But if we had picked a different representative of these cosets, we still better get the same coset on the right. So what we need to show is if A is in UK and B is in VK, then taking AK times BK is the same thing as taking UK times VK, right? So it better be the case that if A is in UK and B is in VK, then the left coset of K containing AB is the left coset of K containing UV. What does that mean? We have to show that the multiplication we're defining here does not depend on the choice of coset representatives. So I'm going to pause and erase, and then I'll explain how that works, and that's the biggest piece by far of proving this theorem. I've kept the statement here, and let's talk through this proof that this operation is well defined. So the key thing that we're going to use is our cosets are the same thing as fibers of this homomorphism. So remember, we are in the case where K is equal to the kernel of a homomorphism. So we know that the left coset of U containing K is the fiber above A for some A and H. So in fact, we know that U is in here, so phi of U is equal to A. So it's the fiber above whatever phi of U is. Similarly, the left coset of K containing V is the fiber above some B. So phi of V is equal to whatever this B is. So by definition of how we defined this operation, UK times VK is equal to UVK. So that's our coset on the right, but that's also the fiber above some element. And since phi of UV equals AB, we know UV is in this coset. So this whole coset, what fiber is it? It's the fiber above A times B. So now we're going to get to this part, where we suppose that we take some other coset representatives. You let alpha be in UK. Remember, UK is equal to the fiber above A. And take beta to be in VK, which, remember, is the fiber above B. And what we need is, if we had chosen alpha and beta as these representatives and written alpha k times beta k, we would have gotten the coset alpha beta k. So it better be true that alpha beta is in the left coset of K containing UV. That's totally equivalent to saying that alpha beta is in the fiber above AB, because we already said that this coset is this fiber. So how do you show that alpha beta is in a certain fiber? Well, just apply phi to it and see where it goes. So all we need is that phi of alpha beta is A times B. And now we're in good shape, because alpha is in the fiber above A, beta is in the fiber above B. So phi of alpha equals A, phi of beta equals B. Phi is a homomorphism, so phi of alpha beta is phi of alpha, phi of beta, which is AB. And we are done showing that this operation is well defined. The rest of the proof that this actually is a group is very straightforward. Why is this operation associative? Because the group operation in G is associative. Basically, what you're going to need is that A times B times C is the same as A times B times C when you think of A, B, and C as elements in G. What is the identity? It's the left coset of K containing 1. And then what is the inverse of the coset G times K? It's the coset G inverse times K. So I will leave the details as an exercise, but they're all pretty straightforward.